Now this circuit over here has a flip-flop also, but we have a pull-down resistor here, so we could have normally low, and we have a pull-up resistor here, and you could tell because the pull-up resistor is connected directly to 5 volts. It's connected directly to high, while the pull-down is connected directly to low. The reason why this resistor was put in so that we could reset the flip-flop. Flip-flops normally has a pin that you could use to reset the flip-flop. And this particular flip-flop, it's active low. So it must normally see high. However, if the pin goes low, it will reset the flip-flop back to the original state which the flip-flop is in when it's powered up. For example, here we have low, so when I push this button we'll have high, so this will cause the output of the flip-flop to change. And here we go. At this point I could use the reset pin and clear the flip-flop back to the original state. If I press this button it will go back to the original state, but just to demonstrate the effect of the reset pin. The reset pin is now high. Whenever I push this button, it's going to go low. The minute the pin sees low, it's going to reset the flip-flop. The LED is going to go off, and this pin is going to go high, which is the pin that was high when the flip-flop powered up in the first place. There we go. And doesn't matter how much time you press this pin again, bring it low as much as you want, nothing happened because the flip-flop has already reset. And as long as it's reset, that's all it does, is just reset. So you would not get a toggle effect by pressing this, bringing this pin low. This is the pin that will toggle back and forth, just like that. Now what is the reset input used for? For example, if you set up your flip-flops as a counter, and say you're counting upwards, and you want your counter to only count to 8, you can place detection in your circuit that whenever the counter reaches 8, it would send this pin low and reset itself. So instead of counting to the maximum value your counter could go up to, you could, stop the counter at a lower number by just resetting it. So if you reset the flip-flop, they'll go back to 0. And this is if you counting upwards. So that is the use of the reset function. Now that we know what flip-flops are and how they function, we can use them to make counters. Before I move on, you must have a clear understanding of what a clock signal is and how our positive edge flip-flop react to it. To refresh your knowledge, a clock signal is a sequence of low-high or high-low, depending on which you start with. This includes button press and release, or a steady stream generated by a clock signal generator circuit, such as a 5-5 timer in a stable mode. Whenever a resistor is used, it will be in either a pull-up or pull-down configuration to satisfy pins that need to be active high or active low, or to generate the clock signal itself. If we're all clear on this, let's move on. This simple circuit generates BCD codes from 0 to 3 and then repeat. The reason why it repeats is because that is the maximum number 2 flip-flops are able to count up to. Here are the formulas that tells you how much flip-flop you need to count up to a certain number. Note the counting start at 0, so counting from 0 to 3 will be considered counting through 4 digits. For example, if we need to count up to 4 digits maximum, we can enter log 4 divided by log 2, and the answer will be 2 flip-flops. Again, this means counting from 0 to 3 and not 4. Likewise, if you have a certain amount of flip-flops and need to know how many digits you can go through, that would be 2 to the power of 2, and that will be equal to 4 digits. And if we need to go to 8 digits, we have log 8 divided by log 2 equal 3 flip-flops. And if we need to count through 16 digits, that's from 0 through 15, we have log 16 divided by log 2 equals 4 flip-flops. Now here, if we have flip-flops, I need to know how much digits a group of them can count up to. We would do 2 to the power of the number of flip-flop that we have, and that would be our answer. So in this case, 2 to the power of 2 flip-flops equals 4 digits. So we could count from 0 to 3. And this one, 2 to the power of 3 equals 8, so we could go through 8 digits here. And this one, 2 to the power of 4 equals 16. So 2 to the power of 4 flip-flops equal 16. So in this case, we would count from 0 through 15. So that's the importance of these formulas. Now let's take a look at this simple counter circuit. We have these two pull-up resistors for the reset pin. When we press this button, this line will go low and it will reset these flip-flops back to 0. Here we have a resistor in the pull-down configuration so that this line will normally be low, and when the button is pressed, it will go high. And it is in a pull-down configuration because the flip-flop react from low to high, so it needs to be, the default needs to be low, and when the button press, it will go high, so it will go in that sequence. Now these are my logic indicators, and they will light up to show the number in the exact sequence as it is right here. So let's give it a whirl. So that's 0, that's 1, 2, 3, and back to 0. So if you look over here, you will see that the indicators actually depict the same sequence. Now, to understand why the circuit is able to count, you have to understand what happened to these flip-flops whenever they receive their clock signal. This flip-flop represents the least significant bit, or ones place. This one represents the most significant bit, or second place. These are the outputs. This output is called Q, and this output is called not Q, or Q not. The not Q output is used to clock each additional flip-flop, and the Q outputs are used to represent our BCD codes. The least significant bit flip-flop is going to change state on every button press. Because these flip-flops react on the positive edge, that is low to high, the outputs of the flip-flops will be different, even though they start out having the same value. Because we have a pull-down configuration here, the clock input is currently seen low. Whenever the button is pressed, this flip-flop will see a transition from low to high and change its output state. At this time, the most significant bit flip-flop will not change its output state because it will receive a transition of high to low. The Q output of both flip-flops will represent the code for 1. If you think about it, the most significant bit flip-flop is currently seeing a high on its clock input, while the least significant bit flip-flop is seeing a low. So when the button is pressed, only the output of the least significant bit flip-flop will be high. The interesting thing to note at this time is that the clock input of the most significant bit flip-flop goes low whenever the output of the least significant bit flip-flop goes high. When you press the button again, the least significant bit flip-flop will switch back to its original state, and the clock input of the most significant bit flip-flop goes high. This will cause the most significant bit flip-flop to change state and give us a high on its Q output. The Q output of both flip-flops now represents the code for 2. Pressing the button again will cause the least significant bit flip-flop to change state, and since the Q output of the most significant bit flip-flop was high, the Q output of both flip-flops now represent the code for 3. At this time, the clock input of both flip-flops will be low by default, so pressing the button again will reset both flip-flops back to their original state. This is the code for 0. The circuit was able to count because the output from one flip-flop is used to control the output of the other. And because they only react to a signal if placed in a certain sequence, configuring a circuit this way will generate the BCD codes necessary to count.